Hi, I would like to do a sloppy practice presentation because I need to collaborate with two people, and I thought it may be a good idea to already show what I've got so we can continue working on it. Alright, so this presentation is called The Error We Make When Inferring a Phylogeny. It's a presentation by me. I'll start off, followed by Giovanni, and in the end Thijs will also contribute a use case. It's on GitHub, you can download it here, and all the source code that made this presentation. So let's start with biology. So there are a lot of species around. So I took 6 crocodiles, for example, and biologists, we are interested in who is related to whom, well, which of these 6 crocodile species are closest related. But even more interestingly, because that's rather easy to solve, but more interestingly, when did those species arose? How many million years back in time? And we do a lot of calculations about that. Alright, so let's say we sequence the DNA of all these crocodiles. We can do that. Let's say this is an imaginary sequence we got from the crocodiles, but from now on it's just 6 abstract species called A to and including F. And this is a DNA alignment of only 40 base pairs. That's just for the presentation. And the 4 base pairs have each have a nice different color. So that's what we can measure in the field, but we cannot directly measure what is the phylogeny in the field. What is the evolutionary relationship between those 6 species, and especially when did all these speciations happen. But we can get the DNA sequences, and we can infer a phylogeny from that. So we can't conclude a phylogeny from it. We have our guesses about it. So I've put 2 approaches here that actually used that DNA alignment I just showed you. Note this is very short because it's a presentation. It can't take too long before I can show my presentation. So here we have a posterior, it's a Bayesian technique in which we sample trees from what is called a posterior, and the likelier trees are present more often. So in this case you don't see a pattern formed yet, but there are three trees overlapping here, and if I would run the simulation a bit longer, then you get a clearer pattern. Spoiler alert, it will be a complete mess for some reasons. Also, we can make a consensus tree. We can say, all right, if that's the posterior, we can just create one consensus tree. Well, this consensus tree gives us completely no information. Apparently the DNA alignment is too weak, which is actually a good finding. So that's what we infer. And the question we ask ourselves is what is the error we make when we infer our phylogenies like this? What is the error? And because we assume, of course you have phylogenetic networks, but let's say we assume that there is a true phylogenetic tree that happened in nature, and we want to see how well these two match. Ideally they would match completely. In practice, also due to stochasticity, they will never overlap completely, but at least we can, but theoretical studies can show the error we make. And actually we've made a tool for that. That's me, Giovanni and Thijs. It's called Pirouette. It's an R package. It's free and open source. You can find it on GitHub. And actually we used it already in this presentation to do all the experiments and show all the plots. So this is the normal pipeline what Pirouette does. There are 4 steps. So initially we as theoreticians, we supply a true phylogeny in nature that can follow any speciation model you'd like. From that tree it simulates an alignment, which you can find in nature. From that alignment it infers multiple phylogenies or posterior phylogenies, and what it does then, it compares these trees with the true tree, and this gives an error distribution. So in this plot, and because there are so little trees it's a bit sloppy, but there have 3 errors have been measured, like it compared this tree with all these 3 using some kind of errors measurement, and this is the distribution of error it gives. So if your inference is good, the errors will be low. So here's the errors 0.28. We cannot judge from only information I just give you if that's much or not much. But ideally it should be zeros, but that's close to impossible. So that's just how it works. You put in a true phylogeny, you put in, and then see, because you also have some assumptions here when you infer your posterior phylogenies. So you put in the true phylogenies, your assumptions, and you get the errors. So in that way we can quantify the error we make in our inference. And that's also biological relevant, because at the moment, by definition, we do our inference with standard models. So a standard model I define here as a model that is part of the tools we do our inference with. For example, BEAS2 is one, or RefBase or MrBase. All these models that are in there, I define them as standard models. And these standard models may not be sufficient in all contexts, because they make assumptions that may not hold in all contexts. And with Pirouette, we can use the pipeline I just showed you to measure the error that's caused by the mismatch between using a standard model, which are in the tools, when nevertheless the truth follows a different model. For example, this tree, let's assume, is simulated using a protracted birth-death model. So the protracted birth-death model is created by Rampal Chen, and especially Rampal Chen, and Rosendale also had some good ideas about it, also influential on that. And this tree, if you use a protracted birth-death model, it assumes, or it implements, that speciation takes time to be recognized. So if a species speciates, let's say close before the present, it's not recognized yet, and that means we'll make an so it may be that there are some species here, but we don't recognize them yet. And that's why we only observe 6 species in nature, where perhaps in reality there are more, because we don't recognize them yet as such. So if you use a protracted birth-death model to simulate a tree, so this is one tree, but of course in an experiment you simulate a lot more, because also there's stochasticity in that process in simulating trees. So if we have a protracted birth-death model in nature, then from that we simulate an alignment we could have found in nature. Then using our standard models that we assume, we infer these phylogenies, which and then we can compare again these two, and we get an error distribution. So in that way we can see if nature has protracted speciation, and we know it does, what the error is we make due to that. There's a caveat on that actually, because this error is caused by multiple things. This error is caused by stochasticity in the alignment simulation. So it may be that there are by chance more or less mutations on some branches that will cause errors. Also the posterior, it's sampled from the complete state space, and the samples can differ, so that means that the trees will differ. That means that the difference between the true and the inferred trees will differ. So that's our 2 sources of errors already. But the interesting source of errors is that we use the mismatch between the true speciation model and the one we assumed. And there's a mismatch between, we used a protracted birth-death model, which was the true speciation model, but we assumed something simpler. In this case we used a birth-death model, which assumes that if there's a new species arises, we immediately recognize this. Well, and we can, so we're mostly interested in this third error or source of errors, and we can actually remove this error, and we call that process twinning. So, well, because the error is caused by the mismatch between the true speciation model and one assumed, in twinning we are going to use a tree. We're going to make this match. We're going to match the true speciation model and one assumed, not on our true tree, but on a twin tree. So here we have a true tree. So this is the protracted birth death model tree, and this is its twin. So notice that the twin has exactly the same topology, so the more closest related species are still closest related, but now it follows a birth-death model, which is the same model that Pirouette assumed in the previous slides. So due to this, and with this tree, we call it the twin tree, we can do exactly the same thing. We can do exactly the same pipeline in Pirouette. So here we have our twin tree. From that we create an alignment. From that we create a posterior, and we compare these and these. We compare the true tree with the inferred trees, and then we get errors, and we get a distribution of errors because we have a distribution of trees. And it is rather predicted that if we do match that the inference assumes a speciation model that's actually gave rise to the true tree, the errors will be lower. And only the errors are now caused by stochasticity in the DNA alignment and stochasticity in sampling the trees. So there's no mismatch between the model, the speciation model that caused this tree, and the model we assumed to cause the tree. So then we get two distributions. We get the error when using a true tree, and we get an error by using the twin tree. And the twin tree error distribution, we call it the baseline error, or the minimum error, or the minimum noise, or whatever. The full error is caused by that baseline error, but also the mismatch between the speciation model. So you see already that the baseline errors, if you look closely from the back, you see that these error values are lower. Actually, they are way lower than here the full errors. And that's very logical, because the true tree I used, the protracted birth death tree, was completely violating the assumption of how speciation worked that I used in my inference. So these distributions, we compare them, and the Pirouette can do that. And like Giovanni and Thijs will also show how it looks like in some nicer plots than I did. But the interpretation of these two distributions is somewhat like this. If the two error distributions are very similar, then our inference is as good as we can. So the standard speciation models, they suffice, and our inference is as good as you can because, well, our priors are just good enough, or they compensate, whatever, they're good enough. Are these distributions very different though, and our inference is bad, we make a big mistake, we make a big error due to using the wrong speciation prior? So one thing how we could solve that is that we add our novel speciation prior to our phylogenetic tools to make it a standard tree prior, and perhaps we should use that one then. So the hardest part is when these distributions are somewhat overlapping and somewhat not, because then we need to use our judgment. So our inference is then disputable, and we can talk about this a lot. It is caused by using the wrong speciation prior, but if it really matters, that's open to discussion. So now, Giovanni will give a talk in which he will talk about the multiple birth model, which is also a non-standard tree prior. He will talk about the biology in a bit more detail and show some preliminary results. After that, Thijs will talk about node sub, which uses a slightly different pipeline, but also still uses Pirouette. He'll describe the biology behind it, what differs with the pipeline I just described, and also show some preliminary results. Alright, so this was the practice presentation, and I wish you a very good day. Bye.